This question is about metal chlorides. Table 2 shows some enthalpy change data. Use the data in Table 2 to calculate the molar enthalpy when calcium chloride dissolves in water. So when CaCl2 solid dissolves in water to form calcium ions AQ and 2 chloride ions AQ, we want to calculate this enthalpy change. What they've given us is a value for forming calcium chloride solid from calcium 2 plus gaseous ions and 2 Cl minus gaseous ions, and they said that that is minus 2237. Then they've given us a value for calcium gas to calcium AQ ions, minus 1650, and they've given us a number for a chloride ion in the gaseous state to chloride ion aqueous. Those are hydration values. We've got 2 chloride ions, so 2 minus 364s. So according to Hess's law, if we want to calculate this and go the other route for the arrow x, then x is going to equal, we're going backwards against the minus, so minus 2237 becomes plus, and then we're going to add minus 1650, and we're going to add 2 lots of minus 364. So we can type that into our calculator. And we get minus 141. You may have learnt a formula, and the formula goes lattice dissociation plus hydrations, but you've not been given lattice dissociation here, you've been given lattice formation, so you would have to turn it in to dissociation, which makes it positive. Use your answer to question 5.1 to deduce how the temperature changes. Now, because my reaction is exothermic, because mine is exothermic, the temperature must have risen when I added my calcium chloride to water. Explain why the hydration of fluoride ions, so that is for F minus gas going to F minus AQ, is more negative than chloride ions. So we're comparing F minus to Cl minus. So F minus ions, be careful not to say fluorine, fluoride ions are smaller than Cl minus ions, so have higher charge density and as a result can form stronger, because dissolving in water is about attracting something in water, stronger attractions. And which bit of water would a minus ion attract? They're going to attract to the delta plus H in water. Figure 2 shows an incomplete Born-Haber cycle for calcium chloride. Complete the Born-Haber cycle by writing the formulas of the missing species on each of the blank 2 lines. So you can see at the bottom we've got our solid ionic lattice, and then we're making it from the elements in their standard state. So that is our enthalpy of formation. That's our value here that's written down as minus 795. Then what we need to do is, we can see that at the third arrow is about turning calcium into a 1 plus ion, that's ionisation. But to do that, we need to have gaseous atoms of calcium. And so we will need to do enthalpy of atomization of calcium. So we're going to change the calcium from calcium solid to calcium gas. We're going to leave the chlorine alone, only one change at a time on a Born-Haber cycle. That one would be plus 193, and that makes sense that the arrow points up. Then we can see they've given us first ionisation energy, 590, and they haven't given us second ionisation energy. That's what we're going to be asked to calculate. That's going to be our x, which is what's happening next. Then the next thing that needs to happen, before we can start making negative ions, we need to atomise the chlorine And so they've given us atomization of chlorine. We're going to leave the calcium alone. We're going to leave the electrons alone. We're going to atomize chlorine. Now, the definition of atomization is when one Cl gas atom forms from the element, but we're going to have to form two here to balance the chlorines. So this arrow up the side is going to be 2 lots of +1, 2, 1. Then we've got electron affinity, -364, where the chlorine atoms become chloride ions by gaining electrons. And then we've got lattice formation, -2237. So the numbers were not part of the answer here. We just had to have the lines, label the lines with the elements and their state symbols. So make sure your state symbols are clear. Make sure the exam board can tell that it's a G, not an S. Make sure that on each line there is no overall charge, so that you've kept the right number of electrons. The next thing we have to do is calculate the second ionization energy of calcium. So there are different ways that you can do this. You could do that -795 is equal to all the other arrows added together. So if I said that, because all the other arrows point around this cycle in a clockwise direction except -795, we could say that it's equal to 193 plus 590 plus the unknown, our x, plus 2 lots of 121 plus 2 lots of -364, because we had 2, so I should put that on there, shouldn't I? 2 Cls, each being becoming chloride ions, plus -2237. And you could work it out by doing the algebra on this sum here. The other way that you could do that, I'm just going to do it in a different colour pen if you prefer to use Hess's law, is that your arrow starts here and ends here, the one you're trying to find. So if you were to go the other way around the cycle, you would get the same answer. So if you were using this method, then what you would say is that x equals, we're going to go down this arrow, so -590, -193, -795. So -590, -193, -795. Up, so +2237. Up the next one, so plus 2 lots of 364. And then down the last one, so minus 2 lots of 121. Now, if you look at both of these sums, they both show the exact same calculation, just written out differently, and both are acceptable. So then you've got to type it all into your calculator. And that gives you a positive answer, which is what you're expecting because the arrow pointed up, and it's coming out as +1145. It says, explain why the second ionization energy of calcium is greater than the first. Well, this is because the second ionization energy, the electron is being removed from a positive ion, so more energy is needed because the attraction between the nucleus and the electron being removed is stronger. Table 4 shows lattice enthalpies based on the perfect ionic model and lattice enthalpies from a Born-Haber cycle for 3 metal chlorides. So our Born-Haber cycle is our experimental values. Our perfect ionic model assumes like perfectly spherical ions attracting each other with only electrostatic forces of attraction. So a theoretical answer. Discuss the values. In your answer, you should compare the 3 values based on the perfect ionic model. So it wants us to compare these 3 values. And then it says compare the values in this direction as well and say what that tells us. So what can we say from the perfect ionic model one? So assuming that they've all got perfect ionic structures, we've got a much larger value for calcium chloride, then we've got silver chloride, then we've got potassium chloride. So doing our first bullet point, comparing perfect ionic model values. Let's just state what we've got. Calcium chloride is greater than silver chloride, which is greater than potassium chloride. What that says is electrostatic forces of attraction are strongest between the ions in calcium chloride and weakest between the oppositely charged ions in KCl. That's the first thing. So and if we look, we can see that the value is much, much bigger for calcium chloride compared to the other two. ClCl2 has stronger forces of attraction between oppositely charged ions so they've all got the same negative ion, but as Ca2 plus ions are more highly charged than Ag plus and K plus. And if you look at the periodic table, they're also smaller, a little bit smaller than potassium because they've got more protons but the same number of electron shells, and quite a lot smaller than silver ions because being higher up in the periodic table. So they are more highly charged and smaller. So Ca2 plus ions have higher charge density and can form stronger attractions to Cl minus ions. So that's our first bit. Okay, so that's our first kind of part of the answer. Okay, so the next bit is to compare the values across the table between the perfect ionic model and the Born-Haber cycle. So we can see that the values for calcium chloride are fairly similar, there's not a big difference. And for potassium chloride, they're fairly similar too. The difference here is 14, and the difference here is 11. But the difference here, 905 minus 770, is 135. So calcium chloride and potassium chloride have fairly similar values in the two different models, but silver chloride has quite a large difference. Why might that be? So CaCl2 and KCl both have similar values from the perfect ionic model and the Born-Haber values, what does that tell us? That tells us that these two must be almost, CaCl2 and KCl are almost perfectly ionic, with very little covalent character. They are perfectly spherical. So the ions are perfectly spherical. And then if we look at AgCl, the values are different, showing that AgCl has some covalent character, this shows that Ag plus is able to polarize Cl minus ions, distorting the ion. So it's not spherical anymore.